Okay. Let me take my PDF. Tree recursion. So another common pattern of computation is called tree recursion. As an example, consider computing the sequence of Fibonacci numbers, in which each number is the sum of the preceding two. So we have 0, 1, 1, 2, 3, 5, 8, 13, 21. In general, the Fibonacci numbers can be defined by the rule 0 if n is equal 0, 1 if n is equal 1, otherwise a recursive call to the function itself for n minus 1 plus the function itself of n minus 2. We can immediately translate this definition into a recursive procedure for computing Fibonacci numbers. Of course, we define a fib that takes an argument. We have two stopping conditions for n equals 0 and n equal 1. And otherwise, if these two conditions are not met, there is this else block where the function itself is called again. Consider the pattern of this computation. To compute fib of 5, we compute fib of 4 and fib of 3. To compute fib 4, we compute fib 3 and fib 2. In general, the evolved process looks like a tree, as shown in figure 1.5. Let's see. And this is the tree recursive process generated in computing for when you want to compute the Fibonacci number for 5, the Fibonacci series for 5. The fact is that, as you can see, what I see from this tree is that you are computing two times, you are calling two times fib of 3, you are calling two times fib of 2, and 3 times fib of 2, 1, 2, 3, and here we have a lot of stopping conditions, of course. Basically, all the branches terminate with the stopping condition. Let's see if the book says something about this. Notice that the branches split into 2 at each level, except at the bottom. This reflects the fact that the Fibonacci procedure calls itself twice each time it is invoked. This procedure is instructive as a prototypical tree recursion, but it is a terrible way to compute Fibonacci numbers because it does so much redundant computation. Yes, that's it. Notice in figure 1.5 that the entire computation of Fib3, almost half the work, is duplicated. Yes. In fact, it is not hard to show that the number of times the procedure will compute Fib1 or Fib0, the number of leaves in the above tree in general, is precisely Fib of n plus 1. To get an idea of how bad this is, one can show that the value of Fib n grows exponentially with n. More precisely, Fib of n is the closest integer to phi to the power of n divided by square root of 5, where this phi is 1 plus square root of 5 divided by 2, approximately 1.6180, which is of course the golden ratio and which satisfies the equation phi squared is equal to phi plus 1. Thus, the process uses a number of steps that grows exponentially with the input. On the other hand, the space required grows only linearly with the input, because we need to keep track only of which nodes are above us in the tree at any point in the computation. In general, the number of steps required by a tree recursive process will be proportional to the number of nodes in the tree, while the space required will be proportional to the maximum depth of the tree. Okay, so the number of steps required by a tree recursive process will be proportional to the number of nodes, while the space required to be so the time, the number of steps is the time in a complexity analysis, is proportional to the number of nodes, while the space is only proportional to the maximum depth of the tree. We can also formulate an iterative process for computing the Fibonacci numbers. The idea is to use a pair of integers a and b initialized to fib1 and fib0, and to repeatedly apply the simultaneous transformations. Basically, a becomes a plus b, and b becomes a. It is not hard to show that after applying this transformation n times, a and b will be equal, respectively, to fib of n plus 1 and fib of n. Thus, we can compute Fibonacci numbers iteratively using the procedure basically, here we are interested in fib iter, where we have the two arguments a and b plus count, and if count is equal to 0, we stop and return b. Otherwise, we call iteratively, we call recursively fib iter. And this method for computing fib of n is a linear iteration. The difference in number of steps required by the two methods, so the difference in the time complexity, one linear in n, one growing as fast as fib of n itself, is enormous, even for small inputs. One should not conclude from this that tree recursive processes are useless. When we consider processes that operate on hierarchically structured data rather than numbers, we will find that tree recursion is a natural and powerful tool. But even in numerical operations, tree recursive processes can be useful in helping us to understand and design programs. For instance, although the first fib procedure is much less efficient than the second one, it is more straightforward, being little more than a translation into Lisp of the definition of the Fibonacci sequence. To formulate the iterative algorithm required noticing that the computation could be recast as an iteration with 3 state variables. So example, counting change. It takes only a bit of cleverness to come up with the iterative Fibonacci algorithm. In contrast, consider the following problem. How many different ways can we make change of $1 given half dollars, quarters, dimes, nickels, and pennies? More generally, can we write a procedure to compute the number of ways to change any given amount of money? This problem has a simple solution as a recursive procedure. Suppose we think of the types of coins available as arranged in some order. Then the following relation holds. The number of ways to change amount A using n kinds of coins equals the number of ways to change amount A using all but the first kind of coin plus the number of ways to change amount A minus D using all n kind of coins, where D is the denomination of the first kind of coin. Let me reread this passage. The number of ways to change amount A using n kind of coins. So for example, we have the amount is $1 and we have a $1 coin, half-dollar coins, quarter-dollar coins, etc., etc. The number of ways to change amount A, so to change a dollar, using all but the first kind of coin, okay, plus the number of ways to change amount A minus D using all n kind of coins, where D is the denomination of the first kind of coin. Okay, I think I got this. To see why this is true, observe that the ways to make change can be divided into groups. Those that do not use any of the first kind of coin, and those that do. Therefore, the total number of ways to make change for some amount is equal to the number of ways to make change for the amount without using any of the first kind of coin, plus the number of ways to make change assuming that we do use the first kind of coin. But the latter number is equal to the number of ways to make change for the amount that remains after using a coin of the first kind. Thus, we can recursively reduce the problem of changing a given amount to the problem of changing smaller amounts using fewer kinds of coins. Consider this reduction rule carefully and convince yourself that we can use it to describe an algorithm if we specify the following degenerate cases. If A, that is the amount to be changed, is exactly 0, we should count that as one way to make change. If A is less than 0, we should count that as 0 ways to make change. If n is 0, we should count that as 0 ways to make change. And we can easily translate this description into a recursive procedure. Let's see this procedure. So the main procedure is count change that takes as argument only the amount to be changed. And that consists in the CC procedure that is defined below, which take instead two arguments. One is the amount and the other one is kinds of coins. We have one condition. There are the condition listed above. And if those conditions are not met, the function calls itself recursively. Then we have the definition of first denomination with kinds of coins, where we have the different kinds of coins, As you can see, the first denomination procedure takes as input the number of kinds of coins available and returns the denomination of the first kind. Here we are thinking of the coins as arranged in order from largest to smallest, but any order will do as well. And we can now answer our original question about changing a dollar. Now, what I notice here is that these definitions are not nested. So, for example, here we have the argument amount is repeated throughout all these different definitions. Instead, I think that if we nest these helper procedures inside the main procedure, we can avoid to specify amount in the argument of this procedure. Let's see if the book says something in this direction. Okay, we can now answer our original question about changing a dollar. Count change of $100, 292. Count change generates a tree recursive process with redundancies similar to those in our first implementation of fib. It will take quite a while for that 292 to be computed. On the other hand, it is not obvious how to design a better algorithm for computing the result, and we leave this problem as a challenge. The observation that a tree recursive process may be highly inefficient, but often easy to specify and understand that has led people to propose that one could get the best of both worlds by designing a smart compiler that could transform three recursive procedures into more efficient procedures that compute the same result. And here we have the first series of exercises. Let's see, a function f is defined by the rule, and we have a stopping condition, and we have the recursive call. Write a procedure that computes f by means of a recursive process. Write a procedure that computes f by means of an iterative process. Okay, this could be an interesting exercise to do. Maybe I will do it. The following pattern of numbers is called Pascal's triangle. The numbers at the edge of the triangle are all 1, and each number inside the triangle is the sum of the two numbers above it. Write a procedure that computes elements of Pascal triangle by means of a recursive process. This is nice as well. And prove that fib of n is the closest integer to phi to the power of n divided by square root of 5. Hint, so we use induction and definition of the Fibonacci numbers to prove. Okay, this is more a math problem. I think I will do for sure exercise 1.11 and maybe just for fun the 1.12. But now let me read this footnote, which seems interesting. One approach to coping with redundant computations is to arrange matters so that we automatically construct a table of values as they are computed. This is the memoization. Each time we are asked to apply the procedure to some argument, we first look to see if the value is already stored in the table, in which case we avoid performing the redundant computation. This strategy, known as tabulation or memoization, can be implemented in a straightforward way. Tabulation can sometimes be used to transform processes that require exponential number of steps, such as count change, into processes whose space and time requirements grow linearly with the input. Okay, see exercise 3.27. In chapter 3 and chapter 4 and chapter 5, things will become very interesting, I think. This is still a lot of theory. Orders of growth. The previous examples illustrate the processes can differ considerably in the rates at which they consume computational resources. One convenient way to describe this difference is to use the notion of order of growth to obtain a gross measure of the resources required by a process as the inputs become larger. Let n be a parameter that measures the size of the problem, and let R of n be the amount of resources the process requires for a problem of size n. Let n be a parameter that measures the size of the problem, and let R of n be the amount of resources the process requires for a problem of size n. Okay. In our previous examples, we took n to be the number for which a given function is to be computed. But there are other possibilities. For instance, if our goal is to compute an approximation to the square root of a number, we might take n to be the number of digits accuracy required. For matrix multiplication, we might take n to be the number of rows in the matrices. In general, there are a number of properties of the problem with respect to which we will be desirable to analyze a given process. Similarly, R of n might measure the number of internal storage registers used, the number of elementary machine operations performed, and so on. In computers that do only a fixed number of operations at a time, the time required will be proportional to the number of elementary machine operations performed. We say that R of n has order of growth. I don't remember how it's called that Greek letter. Maybe it's omega. Oh no, it's theta. I don't remember. I don't remember. I will check later. No, let me check now. Yes, it is theta. Yes, theta. Written R of n equal theta of f of n, pronounced theta of fn, if there are positive constants k1 and k2 independent of n, such that k1 times fn less or equal to R of n, less or equal to k2 times f of n. for any sufficiently large value of n. In other words, for large n, the value Rn is sandwiched between k1fn and k2fn. Okay. For instance, with the linear recursive process for computing factorial described before, the number of steps grows proportionally to the input n. Thus, the steps required for this process grows as θ of n. We also saw that the space required grows as θ of n. For the iterative factorial, the number of steps is still θ of n, but the space is θ1. That is constant. Yes. The three-recursive Fibonacci computational requires phi to the power of n steps and space, linear space, so θ of n, where phi is the golden ratio described before. Orders of growth provide only a crude description of the behavior of a process. For example, a process requiring n squared steps and a process requiring 1000 n squared steps and a process requiring 3n squared plus 10n plus 17 steps all have the same order of growth. On the other hand, order of growth provides a useful indication of how we might expect the behavior of the process to change as we change the size of the problem. For a θ of n linear process, doubling the size will roughly double the amount of resources used. For an exponential process, each increment in problem size will multiply the resource utilization by a constant factor. In the remainder of section 1.2, we will examine two algorithms whose order of growth is logarithmic, so that doubling the problem size increases the resource requirement by a constant amount. Exercise 1.14. Draw the tree illustrating the process generated by the count change procedure in making change for 11 cents. What are the orders of growth of the space and number of steps used by this process as the amount to be changed increases? The sine of an angle, specified in radians, can be computed by making use of the approximation sin x approx x if x is sufficiently small, and the trigonometric identity sin x, okay, to reduce the size of the argument of sin. For purposes of this exercise, an angle is considered sufficiently small if its magnitude is not greater than 0.1 radians. These ideas are incorporated in the following procedures. We define cube, we define P is that what's P? 3x minus 4x cube okay, and sine of an angle if not Okay, if not greater than 0.1, we return angle, otherwise uh, we approximate it. How many times is the procedure P applied when sine is evaluated? Sine of 12.15 is evaluated. What is the order of growth in space and number of steps in space and time as a function of A used by the process generated by the sine procedure when sine A is evaluated? Okay, this could be another interesting exercise. Let me see if it is better to stop here, and the next video will be with a few exercises. Let me see, another exercise, a lot of exercises. Okay, maybe I can do also the paragraph here on exponentiation because there are a lot of exercises, and then I'll stop. Consider the exponentiation. Consider the problem of computing the exponential of a given number. We would like a procedure that takes as argument a base b and a positive integer exponent n and computes b to the power of n. One way to do this is via the recursive definition, which translates readily into the procedure. This is a linear recursive process which requires theta n steps and theta n space. Just as with factorial, we can readily formulate an equivalent linear iteration. That is this, where we have three. I mean, here we need to look at iter, and we have three arguments: b, counter, and product. This version requires theta n steps, so linear time, but constant space. We can compute exponentials in fewer steps by using successive squaring. For instance, rather than computing b to the power of 8 as basically 8 multiplications, multiplying b 8 times by itself, we can compute it by using 3 multiplications. This method works fine for exponents that are powers of 2. We can also take advantage of successive squaring in computing exponentials in general if we use the rule. Okay, this one that changes if n is even or if n is odd. And of course, we can express this method as a procedure, where the predicate to test whether an integer is even is defined in terms of the primitive procedure reminder by this one. Okay, if n reminder if the remainder of n divided by 2 is equal to 0, then the number is even, otherwise the procedure returns false. The process evolved by fast exp grows logarithmically with n in both space and number of steps. To see this, observe that computing b to the power of 2n using fast exp requires only one more multiplication than computing b to the power of n. The size of the exponent we can compute therefore doubles with every new multiplication we are allowed. Thus, the number of multiplications required for an exponent of n grows about as fast as the logarithm of n to the base 2. The process has theta log n growth. The difference between theta log n growth and n growth, so the difference between the logarithmic growth and the linear growth, becomes striking as n becomes large. For example, fast exp for n equal 1000 required only 14 multiplications. It is also possible to use the idea of successive squaring to devise an iterative algorithm that computes exponentials with a logarithmic number of steps. Although, as it is often the case with iterative algorithms, this is not written down so straightforwardly as the recursive algorithm. And here we have the exercises. Design a procedure that involves an iterative exponentiation process that uses successive squaring and uses a logarithmic number of steps, as does fast exp. The exponentiation algorithms in this section are based on performing exponentiation by means of a repeated multiplication. In a similar way, one can perform integer multiplication by means of repeated addition. Okay. Other exercises. And greatest common divisors. So the next video will be showing a few of those exercises. Let me see how many paragraphs are left. We have greatest common divisors. Then we have probabilistic methods. Okay. Exercises, a lot of exercises. I think we are, okay, we are close to the end of 1.2. And then we will have formulating abstractions with higher order procedures. This seems to be very interesting. But that's all for today. So goodbye. See you in the next video. Ciao ciao.